Hello, my name is Dr. Ernesto Lee from Miami-Dade College. Go Sharks. And what I want to do is I want to talk to you about Central Limit Theorem with respect to data science and analytics. So with that being said, let's just jump right in with the definition of the Central Limit Theorem. So the Central Limit Theorem, it basically says that if you take repeated random samples from a population and you calculate the mean value of each sample, then the distribution of the sample means are going to be approximately normally distributed, even if the population that the samples came from is not normal. Now, that to me just sounds like a bunch of words. So let me try to state this in plain English. Effectively, what Central Limit Theorem says is that if I can get the averages of a sample, of a subset of a population, then I can make definitive statements about the overall population. In other words, if I can grab, let's say, 100 people out of 1,000 people, and I can get their average height, then from that I can infer the average height of the entire population of all 1,000 people. That's why it's powerful. The Central Limit Theorem, it basically says that the average of the sampling distribution is going to be equal to the average of the population distribution. Now, the Central Limit Theorem is useful because it allows us to use a sample average. It allows us to only get data from a small part of the overall population, and that allows us to draw conclusions about the larger population. That is why the Central Limit Theorem is so powerful. So let's talk about a couple of examples of the Central Limit Theorem in the real world, because frankly, Central Limit Theorem, it's everywhere. It's everywhere. And I'm just going to give you a couple of examples. If you look in the world of economics, economists are often going to use the Central Limit Theorem when they're using sample data to draw conclusions about a population. For instance, an economist might collect a simple random sample of 50 people in the town, let's say Miami, and use the average income of those 50 people in the sample to estimate the average annual income of everybody in Miami. So if this economist finds that the average annual income of somebody in Miami is $60,000, then her best guess for the true average income of people in Miami, and all of Miami, will be $60,000. If you look at biology, the Central Limit Theorem in biology, biologists, they use the Central Limit Theorem whenever they use data from a sample of organisms to draw conclusions about the overall population of organisms. For instance, a biologist that might measure the height of 30 randomly selected trees in Miami, same type of tree, and then use that sample average height of the trees to estimate the population average height of all trees of that type in Miami. For instance, if they're looking at a royal palm, and they get the sample average of, say, 30 royal palms, and it comes to 25 feet, then that biologist's best guess for the population average height for royal palms in Miami will be 30 feet. If you look at manufacturing and industry, manufacturing plants, they often use the Central Limit Theorem to estimate how many products produced by the plant are going to be defective. For instance, the manager of a plant may randomly select 60 products that are produced by the plant in a given day and count how many of those defective products in the sample to estimate the proportion of all products that are defective that are produced by the entire plant. And let's just do one or two more. Everybody has had surveys. Surveys are counting on the Central Limit Theorem. Let's say I work at Miami-Dade College. Let's say Miami-Dade College sends out a survey of 50 randomly selected employees and asks, hey, give me your overall job satisfaction on a scale of 1 to 10. If the employees in that sample say, hey, my overall job satisfaction is 8.5, then the best guess for the college is that all employees have an average satisfaction rating of 8.5. And just one last one, farmers will often use the Central Limit Theorem. Let's say an agricultural scientist, they want to test a new fertilizer, and so they put this on 15 different fields, and then they measured the average crop yield of each field. If it's found that the average field produces 500 pounds of wheat, then the best guess for the average crop yield for all fields will also be 500 pounds of wheat. So Central Limit Theorem, it's literally everywhere. That's a small sampling, but Central Limit Theorem is everywhere. And so as a data analyst or a data scientist, you must be aware of Central Limit Theorem. You at least have to have an intuition of what Central Limit Theorem is, what it does, because oftentimes we're going to make the assumption that the data that we're using honors the Central Limit Theorem. Let me ask you to do a thought experiment, okay? And here is the thought experiment. What I want you to do is I want you to imagine that you're a fisherman and each day you catch 5 fish. And let's say the fish are all the same type. So let's say the fish, they range in size from 1 inch to 20 inches. What can you infer about the population of fish? About this population of fish? Let me share my screen here. Okay. And what I'm going to do is I'm going to pull up Excel. I'm going to pull up Excel, and I'm going to build a little spreadsheet here. Just need one sheet. And let's say every day I catch 5 fish. Fish 1, fish 2, fish 3, fish 4, and fish 5. Okay? So from these 5 fish, we said that they range in size from 1 inch to 20 inches. So let me say, I'll do a random between. One and 20 inches. Okay. Let's copy this. Paste this here. Okay. And then I'm going to get the average, right, for that day. Okay, so this would be the average for the day. All right, so let's say on the first day I catch 1 fish that's you catch 1 fish. That fish is, expand this here. Let's say that you catch 1 fish and that fish is 19 inches. The second fish is 20. The third fish is 20. The fourth fish is 9 inches. The fifth is 18 inches, and so for that day, the average size of the fish is 17.2 inches. That's day 1. Okay. So let's say day 2. I'll say day 2 is going to be A2 plus 1. A2 plus 1. Okay. And what I'll do is I will take all of this. I'm just going to do Control D. And I realize the numbers change, that's fine, but let's say that we have 5 days, okay? Let's say we have 5 days. So what I want to do is I want to take column G here, and let me insert a histogram with just the average. And if I just look at 5 days, you don't really see a pattern that starts to emerge. And so what I'm going to do is I'm going to delete this for now. What I'm going to do is I'm going to go from 5 days to, let's say, 30 days. Do Control D for down. And now, again, these are the fish that we caught each day. The size of the fish in inches, between 1 and 20 inches. If I take the average after 30 days, I'm going to insert a histogram. Then you start to see a bit of a pattern start to develop. You see some over here are smaller, and some over here are larger. But then you start to see outliers just a little bit. So I'm going to delete this. This is after 30 days what this looks like. Actually, I'll leave this here and call this 30 days. So then what I'm going to do is I'm going to go from, actually it's 29 days, but close enough. I'm going to go from 30 days to, say, 120 days and see if we see a pattern that develops. Let me do Control D to have it go down, copy down rather. I'm going to take the average, I'm going to insert, create a histogram, and if you look at 120 days, you definitely start to see a pattern that emerges. 120 days. You definitely start to see a pattern that emerges here. 5 days, there's no pattern. In 30 days, you begin to see the start of a pattern. Let's say that this fisherman has been fishing for 3 years. Well, let's say this fisherman has been fishing for 1,000 days in a row. Let me go down to 1,000. Go down. So this fisherman has been fishing for 1,000 days in a row. Let's get the average. Let me insert a histogram here. And then you see a really, I'll leave this here, this side here. This is after 1,000 days. Okay, so this was all done kind of just off the cuff, right? Randomly selected this. This is one use case. The amazing thing about the central limit theorem is that it just shows up everywhere in nature, in social sciences, in science, the physical sciences, in business, in finance, in economics. The central limit theorem is one of the things that's foundational to all data analytics. This is one of the insights into the universe right here. Look at this almost perfect bell curve. The data is almost normalized. It's almost normalized. And really what you'll see is that the shape starts to take place at about 30 days here. And the longer and the more data that you select, the more fine-grained you can see. The more fine-grained you can see, this bell curve starts to take shape. Okay. All right. So let me stop sharing my screen. So that was the thought experiment. That's what I wanted you to. That's what I wanted you to see and experience. I would encourage you to do exactly what I just did right there. I'd encourage you to do that to see for yourself. The numbers will be different, but the pattern will be the same. The signal will shine through. So the central limit theorem, it says basically that if you take samples from a distribution, in the example I showed you, we took samples from a uniform distribution where each number has an equal likelihood of occurring, and we found the distribution of the sample mean or average. We see then it will tend to be normal as we increase the sampling to a sufficiently large number. And this again happens everywhere. Think about all of the times in your data set where you'll see an age, or a year, or a height, or a weight, or wealth distribution, or dollars per month. All of these cases and many more are subject to the central limit theorem. It's foundational. You can never be a good data analyst without truly understanding central limit theorem. Okay, so that's the thought experiment. What's the practical insight that you can pull from central limit theorem? Can you come up with a eureka moment, an aha moment? I've said before that if you have a sample size equal to or greater than 30, that's about the threshold that most statisticians say it's sufficient for central limit theorem to hold. As we went from 30 samples to 120 samples to 1,000 samples, the more we increased it, the more we made that data perfectly normal. So sample sizes equal to or greater than 30, they're often considered sufficient for the central limit theorem to hold. And this means that if I have 30 data points, then I can start to trust the data. I can start to pull insights from the data. Let me say that again. If I have 30 data points, then I can start to pull insights from the data. That is a deep insight. Almost all distributions become normal if we create the distribution of the sample mean from a large enough sample. That is the practical insight that you can pull from central limit theorem. Lastly, let's talk about why this is important. Why is central limit theorem important for a data scientist or a statistician? The central limit theorem is used by data scientists and data analysts oftentimes to do what we call hypothesis testing and use that to infer population characteristics from the sample. When I say hypothesis testing, that's something very specific. It's a very specific statistical test. Hypothesis testing is something that's used to check if a hypothesis is true or not. For example, the hypothesis could be going to the gym and exercising and helps in weight loss, or a particular drug cures COVID, or freshmen are more likely to leave college within 2 years. These are all hypotheses that can be tested using hypothesis testing, and central limit theorem helps with that. The other thing that you can do with central limit theorem that makes it important to you as a data analyst or a data scientist is that you can infer information about the overall population with just a subset of the data. Imagine that you, as a data analyst, you want to find the average income of the population of a country, or you want to find the average, let's say, average age in which people live in a certain country. How will you go about it? You're not going to get the age of every single person in the country. So what you're going to do is you're going to get the age of a subset, use central limit theorem to infer the age of the entire country. You can do that with age, you can do that with wealth, with just about anything. But the point is that you can infer population characteristics using central limit theorem. Okay, so that was intended to give you an intuition for central limit theorem. We will use central limit theorem in just about everything that we do in the data analytics course. Hope you got some value from this. Thank you very much.